So hi, good morning everyone. Thanks for coming to the talk. I'm really happy to be at Air2 and I'm looking forward to meeting everyone here. Today's talk is going to be about, well, it's divided into two parts and it's going to be about two different papers. And each of them, they're completely unrelated, but they're both going to be presented at ACL next month. The first one is about a model that is a hybrid model of graphical models and neural networks. And we experimented on this model for the task of morphological tagging. And the second paper is about a model, a fertility-based neural machine translation model for incorporating adequacy or coverage of translations in the neural MT framework. So without further ado, I'm going to jump into the first part of the presentation. And if you have any questions, you can ask, you can interrupt me, or you can ask them at the end of the presentation. A little bit of background about me. I'm a master's student scheduled to graduate at the end of this summer at LTI, and I'm working closely with Professor Graham Newbig and Matt Gormley. I did my bachelor's in Singapore, and I was also in Sweden for a little while. And my research work has been mainly about neural machine translation, prediction of linguistic typologies through representations learned through neural models. A major chunk of my work has concentrated on cross-lingual and low-resource natural language processing for the world's major or remote languages. I'm also generally interested in deep structured prediction models, or models that combine graphical models and neural networks. And I also worked a little bit on neural dialogue generation as part of the Amazon Alexa Prize team for CMU. So before getting into the details of the model, I'd first like to introduce the task of morphological tagging. And I'll describe the baseline model that is a neural model, but which actually performs really well on this task. And through that, I'm going to try to expose some of the assumptions and the faults of the existing baseline model and why we thought of and that's hopefully going to motivate the idea of the neural factor graph model and why we thought of it in the first place. So in the task of morphological tagging, we are given a sequence of tokens in a target language. And for each token, we're going to label it with morphological properties. For example, the first word, which is is the part of speech is a determinant, it's indefinite, the gender is masculine, it's singular, and the pronoun type is it's an article. And we do this for every single token. And so it's essentially a task of multi-output, multi-label classification. Why is this task important? It's important as a first step in the NLP pipeline. So people often do morphological tagging or pause tagging and for the tasks of translation, dependency parsing, and information retrieval. It allows us to get more normalization in the input text. So there could be several forms of the same morpheme, but we would probably like to learn a single representation for them to allow to have a more generalized model. And of course, errors in this part of the pipeline would naturally cascade down to downstream tasks such as parsing. So if we don't perform well on this task, then we're going to lose accuracies on wherever this information is used, like parsing or information retrieval. This task becomes especially hard when we don't have enough annotated data. So if you think about low-resource languages, and there are 7,000 languages in the world. The Universal Dependencies Treebank, which has annotations for these morphological tags, is available for only 70 or 80 treebanks. So this task becomes especially hard when there is no annotated data available, which requires us to think about methods that can do low-resource morphological tagging. And the most common method that people have tried in NLP that generally works really well is training models that combine data from high-resource languages and low-resource languages and training these models together, and that generally tends to improve accuracies on the low resource language as well. So here's another example of, you can assume that maybe Portuguese is the low resource language here, and there's a Spanish sentence, and its translation in Portuguese. So you could, this is a sentence from the Universal Dependencies Treebanks. And you can see that most of the tags are almost exactly the same. But what I would like to point out is the fact that there is gender marking in the Portuguese, in one of the Portuguese sentences tokens, but not in the Spanish sentence. And I'll come back to this point later, but it's important for to note this in order to motivate this model. This suggests that the annotations in languages are not exactly the same. So there might be differences due to linguistic divergences or just the style of annotation of different annotators while they were making tree banks. Maybe I'll now introduce some formal notation for this task in order to describe the models more carefully. So we're given a string of tokens x from x1 to xt, t being the number of time steps, and we need to map it to a string of a sequence of tag sets from y1 to yt. So for the sake of notation, I'm going to represent the morphological properties such as pause, definite, gender as tags. I'm going to call the values that they are assigned as labels, and the sets of properties that are assigned to a specific token as a tag set. And this is the notation I'm going to use to describe everything. So for the task, for this task, for each token, we need to generate a target label, yt, where yt varies from yt1 to ytm, n where we're given a set S of m possible tag types, with the mth type being gender or aspect or tense, which could take a set of values ym, which could belong to, for gender, masculine, feminine, and neuter. And something that's important to note here is that not all tags need to be specified. So for example, here we noted that not all tags are specified for this token, and so on. There might be 20 tags that are represented in the tree bank, but only a subset of them is specified for each sentence or token. And we can assume that the remaining tags map to a null value. So now I'm going to move on to describe the baseline neural model, which tends to perform really well on this task. And this model basically predicts, considers its output space as the set of tag sets that are seen in the training data. So all the tag sets that are seen in the low resource language data, which is very little, as well as the high resource language. The model factorization looks like this. The conditional probability of the sequence of tag sets given the input string is can be modeled as generating a tag set independently at each time step. So this essentially is like a 0th order CRF, because there are no dependencies between the tag sets that are generated at each time step. Like I said, the output space is all the tag sets that are seen in the training data. So we're not predicting tags individually, but a set of tags like pause, gender, and so on all together. So there is no representation, explicit representation of these individual morphological properties in the baseline model. This naturally becomes a problem when we have very little data. Let's say we only have 100 sentences, then we'll only have a limited set of tag sets that we can include in our output space, which deems the model to be not generalizable enough. And this is what the model architecture looks like. First, they use a character level BILSTM to represent a specific word or token, and they extract this representation and then use it in a word level BILSTM that generates the tag set at each time step. The reason for using a character level BILSTM is that it can model morphology much better than word-based models. So that's why character level models are pretty common in morphological analysis. So this is what the baseline neural model looks like. There are several problems associated with this model that I'm going to now discuss. The first problem is that there are several possible tag sets that can be generated for a specific token in a target language. Let's say there are 20 tags, then we could have exponential number of combinations of tag sets that we could generate. And let's say this is the space of all possible tag sets. The training data that we're given when we're doing cross-lingual training is the set of high resource language tag sets as well as the low resource language tag sets. And we're basically constrained to only generate tag sets that belong to this region. We're not accurately representing or generalizing well enough to all the tag sets that could be seen in the low resource language. So this is a very big concern because we're constrained in a very heavy way to, and we're assuming that the tag sets that we could see in the low resource language are going to be exactly the same as the high resource language, which may not be the case. Yes?
Are you assuming that the set of possible tags is the same for all languages?
No, there is no assumption of that sort.
So when you say high resource language text sets, I mean there can be some tags that are not even available in their low resource languages.
Yeah,
Vice versa, there could be some low resource that you've never seen in training.
Yeah, that could be the case.
And the reason some of these are not going to be, some of the ones that are possible but not in your training data are there is because they're just convention of the annotation?
Yeah, there could be divergences. Maybe a specific property is not specified, or the annotations are just different. Maybe gender is just not specified in that tree bank. The Universal Dependencies Treebanks are generally fairly consistent, but there might be cases where features are incomplete or information is missing.
So that's a problem if the test set uses these tags, but the training set does not have them, right? If the test set also misses them, that's not necessarily a problem.
Yeah, if the test set also misses them, that's a problem, right? Because we're never going to be able to generate those tag sets if they're not seen in the training data. So that's the problem that we are trying to tackle.
In practice, how big a problem is this? Like, is the overlap decide? Like, is that an accurate representation of how big the overlap in tag sets is or not?
Well,
just I'm not saying.
Yeah.
In this diagram, I'm just like wondering, is there like 1% of tag sets which aren't matched, or is it like?
So it's a pretty significant. We did like some numbers on what this overlap actually looks like, and it's pretty significant. Like only I guess 80 or 90 of the 700 or 800, so it could be like a big percentage are actually represented in this training data representation. Right. So this is the first problem, and the next problem that you might have also thought of when I was describing the model is that now we're predicting over an output space of tag sets. So these morphological properties are naturally strongly correlated. So we're completely ignoring the fact that the tense could tell us something about the part of speech could tell us something about the tense. If the part of speech is a noun, then it's likely to not have a tense. And properties like tense and aspect are strongly correlated. And there could be several other morphological properties that are strongly correlated, but we're not representing these dependencies in the baseline model. The second issue with the existing model is that there are no dependencies between tags over time steps. So in a language that follows gender agreement, if we see a an adjective which is which has a gender masculine, then we're likely to see that the gender of the noun that follows or is before it is also going to be masculine. But we're not explicitly representing in this this information in the baseline model because, again, we're predicting over tag sets, not over individual tags. So these are the main problems with the existing model. Before I go on and propose the neural fractal graph model, maybe we could think of this relaxation over the conditional probability of the sequence of tag sets given the input sequence by generating each tag individually. But this still has a problem because we're not modeling the dependencies between each tag separately here. So there is still no pairwise dependencies between tags. And the motivation of our model is to basically model variable dependencies between tags over time steps, and also model pairwise dependencies between all tags at the same time step, which brings us to this model architecture. This is a graphical model that takes in potentials from a neural network. So there are several things that are important to note here. This is the series of time steps, and these are the series of tags that are represented in our model. This is basically a factor graph which has pairwise dependencies between each tag at the same time step. So there are pairwise dependencies here, here, and also from the first to the third. And there could be 20 such tags, so there could be several such dependencies. We also have transition dependencies between each tag at subsequent time steps. And additionally, because we call it the neural factor graph, we have unity potentials from a neural network. So we have the green factor is basically a score over all labels of a tag that we obtain from a bidirectional LSTM. And this is very similar to the existing baseline model. But now we're predicting over tags, and we're modeling dependencies, pairwise dependencies over tags, and also transition dependencies between tags. So this is the this was why we proposed this model, and it seemed like an intuitive solution. So the bi-LSTM predicts label scores for all tags. These don't necessarily need to be probability distributions. There are several advantages of this model. The first one is that now we can generate an arbitrary sequence of tags. So we're now we can now tackle the main problem of the existing model, where we're not constrained by the space of tag sets that were seen in the training data. We could essentially generate any sequence of tag sets in this model. One more addition that we make to the model is that we consider all the values that are not represented at a specific time step, all the properties that are not represented to map to a null value. So another sort of interesting thing about this model is this is more interpretable. So this is what I find, I guess, most interesting about the model. Is the fact that we can actually go and probe and look at these factor weights to see what they're learning. We could look at what correlations are there between part of speech and number, and we could see what correlations are there between the transitions from the part of speech labels at a specific time step at the next time step. So this is why we could probably not do this so well in a neural model because it's generally harder to interpret. Yes?
A couple of questions. First, you said you have connection between each pairs of layers here. So if you have 20, you have a cubic, you have a cubic number, so like 400 different.
That's right. Yeah.
Okay. And the second is what's the output layer? Is the green thing or?
So the green thing is just a factor. It's a factor which gets a score from a bi-LSTM model.
So what's the output layer?
The output layer.
I mean, what's the output of the model?
Oh, so the output of the bi-LSTM model, you mean? The output is basically a vector, which is a score for all labels for all tags that we are representing. All labels for each tag. So we would have a score for all possible part of speech tags, all possible gender tags, gender labels, and so on.
How do you compute the pairwise factors?
So we're representing them in our graphical model. I'm going to talk about the inference and learning and decoding of this model in the next few slides. And the last thing is we also obtain empirically better accuracies over a consistent set of languages. Right, so this is what our model factorization looks like. It's the factorization of a general tree-based CRF, I guess. There's a normalization factor, and we're taking a product over all time steps where the C represents the set of factors in our factor graph, and the y alpha is the assignment to the subset of variables that are neighboring to the factor alpha that is being considered at a specific instance. And there are three types of potential functions, like I mentioned before: the neural potentials, the transition potentials, and the pairwise potentials. So yeah, so these are the factor types: the neural, the pairwise, and the transition. These have fairly standard log linear forms. There are some things to note here. We'd like to identify what parameters are we actually training in that large graphical model. We are training the bi-LSTM model parameters. We also have the lambdas that correspond to each type of potential in our model. And so this is the score that's obtained from bidirectional LSTM, F and N. And these F for the pairwise and the transition potentials are essentially indicator functions that give the existence of specific dependency in the model in the training data, in a specific training instance, I mean. Right, so we have this sort of complicated looking graphical model. How do we actually learn it? Performing exact inference is obviously hard. We could have a sequence of 40 tokens and and 20 tags over available in a specific language. How do we actually go about learning this graphical model? So for that, we use an algorithm called the Loopy belief propagation algorithm, which is an approximate inference algorithm, and it's an iterative message passing algorithm that basically works by passing messages from factors, all neighboring factors to a variable, and all the neighboring variables to a specific factor. And it operates iteratively, and by the end of the convergence of this algorithm, what we obtain is marginal probabilities over the labels of a specific variable and the factors as well. The way we measure convergence is by using something called the maximum residual value, which is basically the log of the maximum difference in the messages passed in a specific iteration of belief propagation from the previous iteration. So if there is significant differences in the messages, if there is very little difference in the messages that are being passed in an iteration of BP, then we would consider it to have converged. But something to note here is that it's an approximate inference algorithm. It's not always guaranteed to converge, although empirically we observe that it converges in most cases. So these are standard updates of belief propagation. For messages from variables to factors, we take a product over all the messages from neighboring factors except the factor that we're sending the message to. And for messages from factors to variables, we compute the product over the factor weight, as well as a product over all the neighboring neighboring variables except the variable that we're sending the message to. And this is the standard way that belief propagation works in. We keep on sending these messages from all possible combinations of all possible pairs of neighboring factors and variables in our large graph. And at the end of the convergence of this algorithm, we can obtain belief values, which are essentially the marginal probabilities over variables and factors. And the way we obtain those are the belief value of a variable is basically the product of all the messages that are passed at the end of the iteration of BP from all neighboring factors to that variable. And for the belief value of a factor, it's basically the weight of that factor and all the messages from all neighboring factors to that, neighboring variables to that factor. So at this point, we have approximate marginal probabilities over the variables and factors in our neural factor graph model. And we can now start thinking about how we actually going to update and learn this model. So we learned this model end to end. The parameters that we need to update are the lambda GKs, which are the weights in our probabilistic graphical model, where G varies from G could be a neural network, transition, or pairwise potential. And the updates look fairly standard, look like fairly standard updates for a CRF. They're the expected, the observed feature values subtracted by the expected feature values under the model's approximate distribution as represented by the belief values of that we obtained after doing inference. So now we have the updates for all the lambdas or the weights in our graphical model. We would also like to backprop through the bi-Lestian parameters, and the partial derivatives for that also look very similar. We have the feature values subtracted by the expected feature values under the model's approximate distribution, represented by the beliefs that we get after performing. Yes.
Sorry, to back up a little bit, you're still in that same single low resource language setting, right? Or are you doing any kind of transfer from high resource languages to?
Yeah, so we could think of this model as being used in monolingual or cross-lingual settings. We performed experiments for both, where we use data from a specific low resource language, or we could use data from high resource and low resource language. You could imagine that the method would benefit more from using data from a high resource language as well, because we would be modeling more dependencies pairwise or transition in that high resource language, which is likely to benefit the representations or the predictions we make about the low resource language.
Yeah, but that's not very straightforward because like you'd have to introduce some kind of parameter sharing between these two languages on the input side, as well as the tag sets might differ and so on, right?
Yeah, so the difference between tag sets is not a concern anymore because we're predicting over tags. But we do have language-specific parameters. That's not completely necessary, but that's likely to improve our performance because we would learn parameters that are specific to one of those high resource or low resource languages, and some generic language parameters which correspond to both those languages. I'm going to talk about that in a little bit. So we talked about how we would learn this model. We can also discuss how we would perform decoding. So the way we perform decoding is using a minimum base risk decoding model for a Hamming loss over all the tags. So we would essentially pick the label value with the maximum belief during the time of decoding. We have a belief value over all labels of a specific tag, and we pick the label with the maximum belief value at test time. Right. So language-specific weights, we we train general and language-specific parameters for the transition and pairwise weights in our model. So this basically means that we would have lambda gen and lambda lang, which corresponds to one of those two languages in a cross-lingual setting. Lambda gen is meant to learn the general trends that are standard across both languages, and lambda lang is supposed to learn the exceptions to these trends. So you could imagine like two languages such as Spanish and Portuguese. They might be very similar in certain linguistic characteristics, and we would expect the lambda generic parameter to learn these general trends, and if there are any exceptions to these trends, we would expect lambda lang to learn the exceptions in Spanish or Portuguese, depending on the parameter.
How do these fit in the model that you described before?
Yeah, so that's the next bullet. Yeah. So we sum both parameter matrices to calculate the transition and pairwise factors. And the way we do this is whenever we are doing inference, we would basically just sum the lambda generic or lambda language specific parameter and then use it in the inference procedure. Does that make sense?
Yeah, so when you're training, you have two different data sets. One that's only for the target language, and another for all other languages?
No, so we're training models for two languages at a time in a cross-lingual setting. So this parameter would be a parameter for both those languages, whereas this one would be for the for a specific language. So yeah. And when given, like, let's say we have a Spanish-Portuguese model and we're given a Portuguese sentence, then we would pick the parameter that corresponds to Portuguese here and add it to the generic parameter that is standard across Spanish and Portuguese. And we do the same for the pairwise factors as well. Right, so this was mainly the description of the model. We talked about learning and decoding and performing inference on it. We can discuss the experiments in a little bit. The way we perform experiments for this, we follow pretty standard settings that were taken in the baseline model, where we take a high resource language and a low resource language, which are generally from the same language, family. And we pick the Uralic, Slavic, Romance, and Germanic language families. And we have Finnish, Hungarian, Russian, Bulgarian, Spanish, Portuguese, and Danish, Swedish. Since they're not essentially low resource languages, Hungarian, so the second language is meant to be the low resource language. Hungarian, Bulgarian, Portuguese, Swedish are not necessarily low resource, but the way we simulate them, simulate low resource settings is by restricting the data set size of the second language to be 100 or 1,000 sentences, and we perform experiments for both settings. And these are the data set sizes, so you can see we have like quite a lot of variation in the amount of data that we have in the high resource language, and the low resource language data is again either 100 or 1,000 sentences in addition to this high resource language training data set size. Right, so some details about some things that we needed to keep in mind while training this model, some things that were essential to do to make this work. We realized that belief propagation is a pretty slow algorithm. So it sometimes, when the graph is very large, there are several tags in the training data, and the sentence is really long. It can take really long to perform BP. So we resorted to doing batch-wise BP, where we take a batch of sentences of the same length and then obtain marginal probabilities for those, for all the variables and factors factors in our model. And this was very important for speeding up the inference procedure. The convergence of BP was measured by looking at the maximum residual value, which is the largest change in the messages from two subsequent iterations. or when 40 iterations were completed. Another important thing was to initialize all the transition and pairwise parameters to 0, and this was very important to ensure stable training of the model. And we also needed to upsample the low resource language data by 10 times to avoid overfitting on the high resource language. And we do this for both the baseline and the proposed model. So moving on to the results, we performed experiments in 2 settings, monolingual and cross-lingual. Monolingual, where we constrain where we only have the low resource language and the training data set is either 100 or 1,000 sentences. Cross-lingual settings where we have all the data from the high resource language and only 100 or 1,000 sentences in addition to that, to the high resource language data. I should also mention something about the evaluation metrics. We generally people use 2 evaluation metrics for this task, the F measure and the accuracy. Now you could imagine that a model which predicts over tag sets would generally get better results on accuracy because it would do exact match accuracy on the over tag sets. But since we're predicting over individual tags, if we get the tag set partially correct, then the F score would give partial credit for that prediction. So intuitively, F score might be more suited, better suited evaluation metric for this task. But we reported both results for the sake of completeness in our paper. In terms of the monolingual results, we're able to outperform the baseline model in F measure on all languages that we experimented with. We do slightly worse on accuracy because of the reason I explained. We're no longer predicting over tag sets, so we're basically exploring an exponential space of tag sets in a polynomial amount of time, and the gains are seen in the F measure, but obviously we do not outperform the baseline model in terms of exact match accuracy. Yes.
In the accuracy case, is it just because the tag sets for those particular languages are very correlated to? Oh, sorry, this is monolingual. Sorry.
Yeah.
Sorry.
Yeah. But I guess your question might be valid here as well. So this is the cross-lingual setting. What was your question again?
So just like where your model fails to be more accurate, is it just that the tag sets of the 2 languages are much closer together?
Yeah, it could likely be the case, or simply, the fact that now we have 1,000 sentences, or there could be more overlap between the tag sets that are seen in low resource and high resource language. But that's still not a general and accurate enough representation of all the possible tag sets that could be seen in that low resource language. The annotations there are only still a limited number of sentences in these tree banks anyway. We can't constrain ourselves to only generate tag sets that are observed in these tree banks. So yeah, these are the cross-lingual results, where we see the highest improvements in the case of languages where we have a lot of tags, and we have where the languages have richer morphologies. So Finnish-Hungarian was an interesting case where we obtained really good improvements when when target size was 1,000, and we also obtained really good improvements in the monolingual setting. In the case of Hungarian, when target size was 100, and this is likely to be the case because we hypothesized that our model might have been able to exploit the pairwise and transition dependencies that were represented in our model, and that might have helped the performances. Yes.
Sorry, I just wanted to clarify. For your experiments, you simulated the low resource language by dropping out tags within sets, or are you dropping out whole instances from that language? Like what?
So
what's the simulation?
The simulation only constrains the number of training instances that are added to the training data. So there are only either 100 or 1,000 sentences in the simulated low resource setting.
Okay.
Right. So we also performed an ablation study in addition to the main results, where we tried to observe what happens when we remove the transition factors or the pairwise factors from our model. And we do this for both monolingual and cross-lingual settings and observe a drop in performance whenever we remove transition or pairwise factors. This drop is smaller for the case of the, well, it's pretty equal in both settings, but it seems from the observed drops in performances that pairwise factors are actually more important in improving performances over the transition factors. But of course, including both these factors is what gives the best performance. Now, another interesting aspect of the model, which is, I guess, a really good advantage over neural baselines, is that we can observe and look at what the model is learning. So we can generate a heat map of the transition factors. So these are the learned transition factors for the Russian-Bulgarian model, and we observe several characteristics that we would expect to learn in the model, such as nouns, like determinants are followed by nouns, and adjectives are followed by nouns, and so on. There are several characteristics that you could observe from this heat map if you looked more closely. Yes.
What are the colorings? What are the values that are being used to generate that?
What are the? So those are the lambda
The lambda values.
lambda transition values.
Darker, lighter is.
Darker is stronger. Yeah, and this is at the previous time step, and this is at the next time step. Right, so we could also represent the pairwise factors. So this is the pairwise factor for verb form and tense, and we notice that we know that infinitive verb forms don't have tense. So there's a strong correlation between infinitives and null. And similarly, we could also look at the language-specific parameters that we had in our model. So this is the case for the Russian-Bulgarian model, where we represent the gender-tense correlations. Now, Russian doesn't have only has gender-specific verbs in the past tense. So there is strong correlation between past and all the different genders. But in all other tenses, there is stronger correlation with the null gender, because gender is usually not specified except for the past tense. Yes?
Is there any reason you only consider pairwise potentials? Or was it just an efficiency thing that you did not consider higher order?
Yeah, it was mainly an efficiency thing. There could be, we could represent higher order dependencies, but that would make the model probably more intractable, and performing inference would be really hard.
Yeah, from your example that you said, the POS tag is related to the gender as well as the tense. So you have those triplets.
Yeah.
You consider.
Yeah.
You could imagine.
Yeah, it might actually give some boost in performance, but it would be a very slow model then. That's the only constraint. Yes?
So other extreme of that question is, did you consider dropping some pairwise potentials if the range is kind of flat?
Yeah, we thought about that. We didn't actually experiment with it, but that's something that we considered as well, because some pairwise potentials might just be unimportant in the representation of the model. Right, so these are some recent experiments we're also doing. We're trying to also incorporate morphology into dependency parsing. And these are just, this table is just meant to illustrate the fact that morphology actually helps in neural dependency parsing. So once we add morphological information, it consistently helps in several languages. And we're trying to incorporate our model into an existing state-of-the-art dependency parser model as well. So as a conclusion, we proposed a novel framework for sequence tagging, where we use a hybrid model of factorial CRFs, and we obtain unary potential scores from a bidirectional LSTM. Through this model, we are able to exploit the expressiveness of neural network representations, and the graphical model approach ensures that we have more interpretability in our model, and we can exploit the variable dependencies as desired and as represented in our graphical model. We obtain empirically strong performances on morphological tagging, but I would like to point out that this is a very general framework that could be applied to essentially other sequence labeling tasks, such as semantic role labeling and several other multi-output or multi-classification tasks. And we're also recently doing experiments for doing joint lemmatization and tagging within the same framework. Right, so the main takeaway from this presentation, I guess, would be that well, graphical models and neural networks are the hybrid models of graphical models and neural networks are good for improving performances, as has been shown in previous work on named entity recognition, tagging, and this work. They allow us to represent domain-specific knowledge about the task in our model, like we model the pairwise and transition dependencies. And they also deem the model to be more interpretable, because we can go and actually probe the model to look at what it's learning, which is sort of a big advantage over only neural models. Right, so thank you. If you have any questions, you can ask me now.